this sets the stage to talk about vapor pressure, what vapor pressure is, and how it can help us figure out what's going on with boiling point. Um, Really, I mean, we've discussed this in chapter 5. Vapor pressure is essentially the partial pressure of a gas which is in equilibrium at a particular temperature with the liquid phase. So what do we mean by that? Consider that you have some kind of like a liquid in an Erlenmeyer flask, and let's say it's a liquid, so you have molecules within that liquid. Okay, and let's say this is an open system. All right, so open system means that at any given point of time, these molecules, if they evaporate, they would actually leave the surface, and there'll be air molecules here. Right, so how would this affect the liquid? Like I said, eventually this whole liquid can just evaporate away because this is an open system. So that's why if you take a tumbler and you put a little bit water in a week's time, even during winter time, that water just disappears. It just evaporates off. Now let's compare this to a scenario where you have a flask. Maybe it contains the same liquid, but now I have stoppered it. Okay, so it's closed. So this is a closed system. So you still have the same liquid. You have the molecules, and the molecules are becoming, they're getting into the vapor phase. But the point now here is that the liquid molecules will evaporate as they did in the previous open case. However, because of this seal, they basically have nowhere to go. They can't really escape into the atmosphere. And so as the liquid molecules, it could be water, as those enter in the gas state, some will also start condensing back. Right? So there will be a partial pressure at any given point of time, which will be due to the presence of these liquid molecules, which are now in the vapor form, of course. There will be pressure exerted due to that, and that pressure is what will be referred to as the vapor pressure. Now, what's really important to realize is that as time progresses, as the rate at which the liquid molecules get converted into the gas form, so as the rate of evaporation increases, since they really have nowhere to go, rate of condensation will increase as well. Rate of condensation will increase as well. So that means if we are not changing the temperature, essentially the rate of evaporation will be constant, and eventually one can envision that the rate of condensation and the rate of evaporation, both of those would be equal, and at that particular point of time you would say that a dynamic equilibrium has been reached. So you can say that if the rate of forward reaction, that which is evaporation, is equal to rate of backward reaction, which is condensation, you would say that equilibrium would have been reached. And that's a pretty important point to note. Rate. R is for rate. So the pressure, again, the pressure of the gas when this dynamic equilibrium has been achieved with respect to its liquid phase, this pressure is what is called as the vapor pressure. And so if you think about it, it obviously depends on the nature of intermolecular forces of interaction. Reason being, if you have more of a nonpolar compound which doesn't really tag along with another molecule, so if it has only London forces, those molecules will fill up the space on top of the liquid much more faster as compared to molecules such as water, which have hydrogen bonding, which is a strong force of interaction. So weak intermolecular force that results in volatile substances with high vapor pressures. So things like gasoline, for example, that you pump in your gas tank, or paint thinner, any volatile organic compound, that benzene, cyclohexane, pentane, all of these will have higher vapor pressures, and all of these are also very non-polar compounds. On the other hand, water, which has hydrogen bond for the HOH, that has a strong force of interaction. Consequently, that results in a lower vapor pressure, and it will require a greater amount of energy to break those forces of interaction and get those molecules to be in the vapor phase. Now, the vapor pressure can be measured by connecting a manometer with whatever your closed container is. So point A, figure A, essentially gives you the open system. So here the molecules are escaping, so you can't really do much about it. You can't really measure the vapor pressure due to these molecules, because of course the equilibrium has not cannot be measured in this particular case. Of course, also see the notice the level of the liquid is lower in this case as well, because eventually you expect this liquid to evaporate off. On the other hand, if you have a closed system, in that case, now if you connect that to a manometer, the difference between the levels is going to give the equilibrium vapor pressure, because that would be the pressure at the pressure of the vapors, where the rate of condensation and the rate of evaporation becomes equal. Now, as we talk about that, hopefully you do realize that there is a temperature dependence of vapor pressure and boiling point, so those are related. I mean, if you think about it, we discussed the example of hexane, or maybe gasoline. That's the best example because you can kind of relate to that. So gasoline is it contains 9 carbons. It's nonane, so C9H20, and that's the major component. So it contains carbon and hydrogen. That means it has only London forces. It's non-polar. And that would mean that the vapor pressure should be high and the boiling point should be low. I say that the boiling point should be low because boiling point is defined as that temperature at which the vapor pressure becomes equal to the outside external pressure. And so if the external pressure happens to be 760 millimeter mercury, which is 1 atmospheric pressure, essentially one can envision that molecules with lesser forces of interaction would be able to achieve that pressure faster, and hence the boiling point is going to be low, because the population density on top of this liquid is going to be extremely high. Compare that to a scenario like water. In that case, because the vapor pressure is so low, because of hydrogen bonding, one molecule is tethered to another one through hydrogen bond, and that's really a three-dimensional effect. So the number of molecules that are actually in the vapor phase is very, very low. So you will have to supply enough energy for these molecules to accept the energy and essentially go through the breakup of the hydrogen bonds so that it frees up the water molecules, and that's when the vapor pressure, the internal vapor pressure, will become equal to the external vapor pressure. That means you have to heat the sample, and so the boiling point in this case is going to be high. So high boiling point means vapor pressure is low, and that means we are dealing with polar molecules, strong forces of interaction. Forces of interaction. That means hopefully you were able to see that with the supply of temperature, we would be able to break the forces of interaction, strong forces of interaction, because we would be able to provide the energy for this process, and in the process then the appropriate vapor pressure would be reached. This is what these curves essentially show us. I want you to look at the green curve first, which is the curve at the lower temperature. And essentially what we are looking at is the number of molecules under that curve versus the kinetic energy. So the threshold energy, the fraction of molecules which have that threshold energy, is very, very minimal. On the other hand, as you increase the temperature, essentially the curve kind of gets more flatter, and that means that there is greater number of molecules which are now which have the sufficient energy which is required to escape the liquid phase. So greater the temperature, lower the boiling point, greater will be the fraction of molecules in the sample that will have sufficient kinetic energy to break free and go from the liquid phase to the vapor phase. So realize, in order to go through that phase change, a fixed amount of energy is required, and if the temperature is low, very few molecules actually have that energy to go through this. As you increase the temperature, essentially the curve flattens, similar to the Maxwell distribution, and so it ends up being a greater number of molecules with that minimum threshold energy which is required for the phase change to go through. So hopefully you can realize two things from here: that the numerical value of the vapor pressure is dependent on the magnitude of intermolecular forces. Weak intermolecular forces imply more, less boiling point, more vapor pressure. More vapor pressure, less boiling point. And strong intermolecular forces would mean the opposite. That would mean that it has less vapor pressure. That would mean it has higher boiling point. And the other factor that will decide the vapor pressure will be the temperature, of course. Higher the temperature for that same compound, higher the temperature, greater will be the vapor pressure, and so larger fraction of molecules would have the sufficient amount of kinetic energy which is required to escape and go from the liquid to the gaseous phase. And this is reflective in that water in a bowl example that I was talking about. During winter time, if you take maybe 10 milliliters of water and you put it in an open bowl, let's say, it will take forever to evaporate off. On the other hand, during summer season, it's going to go a lot faster, and the difference in temperature basically explains that during the winter time you have lower temperature, and so the vapor pressure is even lesser. First of all, it's water, and now it's cold water, so a very small fraction of molecules have the energy to go from the liquid phase to the gaseous phase. And of course, during the summer season, it's the opposite. The fraction increases, and hence the vapor pressure increases during the summer months as well. There's a direct connection. All right. This can be studied, this relationship between the vapor pressure and the temperature can be studied by what is called as the Clausius-Clapeyron equation, which in a single point is given as natural log of vapor pressure is negative change of delta, change of enthalpy of vaporization divided by R times 1 over T plus C. So if you notice, this is similar to y is equal to mx plus b. And so if you think about it, if you plot natural log of this vapor pressure versus 1 over T, so if natural log of vapor pressure is plotted against 1 over T, where T is the temperature in Kelvin, R is the gas constant, 8.314, C is the intercept here. Essentially, you should get a straight line, which should eventually hit the Y, and whatever value you get from the intercept, that will be the value of C, which is a constant characteristic for each substance. And if you try to find out the slope of this straight line, essentially from there you can determine the heat of vaporization, because that slope M is going to be equal to delta H vaporization over R. Realize this negative sign basically tells you that it's a negative slope, so the negative and negative is going to cancel off anyways. Now, I have to say that you can, if you wanted to, essentially calculate the heat of vaporization for any liquid by taking various different vapor pressures and measuring those at various different temperatures. Get the graph and use the Clausius-Clapeyron equation. So your experiment would just be measuring the vapor pressure at various different temperatures, and it could be as simple as connecting it to a manometer and go with that. It could be as simple as that. And when you get the graph, so let's say you plotted and you got this graph, which is kind of like the straight line, you determine the slope, the negative slope, and since that slope is going to be delta H vaporization over R, negative sign again is for the negative slope, you would be able to determine the heat of vaporization for any given liquid, which is a pretty important piece of information. Now, the Clausius-Clapeyron equation can be extended in a two-point format, where let's say you knew you had information about the vapor pressure at a certain temperature. So the vapor pressure was, let's say, P1 at a certain temperature T1, and there was another vapor pressure P2 at a certain temperature T2. You would be able to take advantage of all of this data and use the two-point version of the Clausius-Clapeyron equation, that natural log of P2 divided by P1 is equal to delta H vaporization over R, which is the gas constant. The value here is 8.314 times 1 over T1 minus 1 over T2. And if you just wanted to take a look at how we got it, all you have to do is go back to the 1 point equation and we can derive. So I'll just do that for you in a second. Now, the generic form of the Clausius-Clapeyron equation for a single point is natural log of the vapor pressure is equal to negative delta H vapor, so heat of vaporization, divided by R times 1 over T plus C. And of course, that comes from the fact that vapor pressure and temperature, they have a direct relationship, but actually the relationship is not linear. That means that if you double the temperature, it's not that the vapor pressure is going to double as well. That relationship is actually, that number would actually be more than just doubling the vapor pressure. So it's an exponential relationship. So at any given point of time, one can say that the vapor pressure is equivalent to some beta maybe times exponent of negative delta H vapor over RT. And so if you take natural log of both the sides, you would have natural log of P is equal to natural log of beta. This beta is some constant for, the given material, plus natural log of e to the power of, or exponent to the power of, however you want to write it, negative delta H vaporization over RT. And so the exponent and the natural log are going to cancel off, and you're going to see the relationship take up a new format. Natural log of P is negative delta H vaporization over RT plus the ln beta. I have given that a new form, which is C here, which is characteristic of the material, of the liquid that you're using. So again, realize earlier we discussed that this equation has taken a similar format as y is equal to mx plus b. What's really important to understand here is that it's not that you are plotting vapor pressure against temperature. The relationship between temperature and vapor pressure is not linear. It is exponential in nature. It is the natural log of vapor pressure which is being plotted against 1 over T, which is why you get the negative slope that I was discussing earlier. So now if you have one equation, let me erase, make more room here. If you have one equation at, let's say, specific pressure and temperature, you would be able to say that natural log of, let's write that natural log of P1 is equal to negative H vaporization over R 1 over T1 plus C. And you can write down the same thing at another vapor pressure, P2, and that would, of course, be taken at T2, 1 over T2 plus C. So now you have two equations, equation 1 and equation 2. And you can just go equation 1 minus equation 2. Equation 1 minus 2. Let's see what you would get. Or you can do 2 minus 1 if that's what you like, if that's what you prefer. You can do 2 minus 1. Let's try 2 minus 1 just for the sake of argument. Natural log of P2 minus natural log of P1. That will be on the left hand side. On the right hand side, you would have minus H vaporization over R. If that is common, then you can say that it will be 1 over T2 minus 1 over T1. There will be a plus C component and there will be a minus C component, so those two will get cancelled off. And now you can improvise it in the format that we have. Since this is a subtraction, you can consolidate that as natural log of P2 divided by P1, because when something is divided and you take the log of that, it shows up as a subtraction. When something is multiplied and you take a log of that, you use the addition. And since you have a negative sign right outside, you might as well be able to change the order in which these appear. So delta H vaporization over R 1 over T1 minus 1 over T2, which is the format that we have written the Clausius-Clapeyron equation in. So let's put things in perspective, and then we'll solve a couple problems here. Let's go over the concept of vapor pressure and normal boiling point. Normal boiling point is the temperature at which, or boiling point is the temperature at which the vapor pressure becomes equal to the external pressure. And when this external pressure happens to be exactly 1 atm, we use the word normal. So normal boiling point will be the boiling point when the external pressure is 1 atm. Realize the concept of boiling. If you are in the mountains, let's say you're in Colorado or Denver, that area, it would actually take, since the external pressure is going to be lesser than the external pressure in, let's say, Florida, which is at sea level. So since the external pressure is less than 1 atm, it's easier for water to boil. And in fact, water boils at 94 degrees Celsius in the mountains. And so a lot of times you would realize that it's really difficult to cook things completely because the water is boiling, it's coming to a boil at a temperature lower than when it's supposed to be, and that's not enough for the food to cook. So a lot of times you would see that if you have, rice or lentil or something like that, you would have to heat it longer to be able to cook that. So it takes longer for us to cook pasta or whatever is your favorite, boiled food in general, if you're doing it just in a closed vessel, because the external pressure is lesser, and so the material is going to come to a boil faster. In order to solve this problem, you can use a pressure cooker, of course, which is a completely closed system, and so the pressure will be released only once the cooking is complete. Now, if you were to compare the vapor pressures of various different liquids, at various different temperatures, just to kind of give you a perspective here. So if you plot vapor pressure against temperature in degrees Celsius, let's say, and you have something like maybe diethyl ether, you have ethanol, maybe you have water, and you have ethylene glycol. So let's consider that's 800. So 760, which is 1 atm, is somewhere here. This is 1 atmosphere. So I said that we are going to take diethyl ether, which is very volatile, by the way. We know that. And we have ethyl alcohol. So ethyl alcohol, that will have hydrogen bonding. It boils at around 78-ish or so. Water, of course, will have hydrogen bonding as well. And then you have ethylene glycol, which has an OH and an OH. That's the structure. So you have two sites for hydrogen bonding. So you expect the boiling point to be way higher. Since the vapor pressure of diethyl ether is usually high, the curve also looks like that. So it comes to boil around 34.6 degrees Celsius. If you consider ethanol, that will come to a boil at 78.3 degrees Celsius. Water, of course, we know is going to boil higher, so it's going to be at 100 degrees Celsius. And ethylene glycol will have the least, vapor pressure, and that means that the boiling point is going to be furthest out, and it's going to be higher than the 100 degrees Celsius for water. So hopefully you can see that in this case, as we increase the temperature, the vapor pressure for all of these, irrespective of what kind of force of interaction there is, essentially the vapor pressure does rise, because higher thermal energy increases the number of molecules that will have enough energy to vaporize. And because of the shape of this thermal energy distribution curve, essentially small little changes in temperature will have extended bigger changes in case of the vapor pressure. So you can hopefully see that if you take, let's say you're going from temperature of, so if this was, maybe this is 15, if this is 34, That's around 35. So in going from 15 to maybe 20, notice that, or in going from 15 to 20, or you can even have a smaller interval, the change that you see in case of the vapor pressure is going to be pretty dramatic. And for that reason, we say that it's not really, like a linear relationship between the temperature and vapor pressure, something I was discussing early on as well when we first talked about the Clausius-Clapeyron equation. It's more than that. It's an exponential relationship, which is why we would say that at any given point of time, as you increase the temperature, the change in the vapor pressure is going to be dramatic. Okay, let's go over a problem set here. The question is the vapor pressure of ethanol at 34.7 degrees Celsius is 100 millimeter mercury. The heat of vaporization is provided as 38.6 kilojoules per mole. What is the vapor pressure of ethanol in millimeter mercury at 65 degrees Celsius? So some information is provided to you and rest is, asked. It's a good idea in a numerical problem since you would see a lot of big formulas this semester. And of course, I'm going to provide you the formula sheet, but you should still know which equation to follow, which equation to use. So you need to first sort the information that is given to you. So sort that information. You are given the initial temperature in degrees Celsius as 34.7 degrees Celsius. You're also given the pressure, vapor pressure corresponding to that, which is 100 millimeter mercury. Delta H vaporization is 38.6 kilojoules per mole. The second temperature, again in degrees Celsius, is given 65 degrees Celsius. So one thing that you should strike is that we are increasing the temperature. So if we are increasing the temperature, the vapor pressure is also supposed to increase. So we have to determine P2. What is the second pressure? Of course, we know the Clausius-Clapeyron equation according to the two-point format. It's natural log of P2 over P1 is equal to negative delta H vaporization over R. And if you're putting a negative sign here, then you better put a T2 minus T1, or you can write it as a positive sign outside, and so this will become T1 minus T2. However you want to do it, both of those are accurate. The first thing I would say, since both the temperatures are supposed to be in kelvins, it's a good idea to convert the degree Celsius into Kelvin. And the way we do it is we add 273.15 to both of these numbers. So add 273.15 to 34.7, add the 273.15 to 65, 273.15, and that will give you the value in Kelvin, which is what you would want to plug into your Clausius-Clapeyron equation. Also realize the value of P1 here is 100 millimeter mercury, and that just means that the value of P2 that you're going to get at the end of the day should also be in millimeter mercury. The value of R, the gas constant, is 8.314. Delta H vaporization, since we are dealing with Kelvin and millimeter mercury, you should convert the kilojoules into joules, because the value of R is in joules per mole per Kelvin. So the Kelvin and Kelvin will cancel off, of course. So your number should be in joules per mole rather than kilojoules per mole. So this is going to be negative 38.6 times 1,000 here. So let's start plugging in the values and let's see what we get. So upon the addition of 273.15, the Kelvin temperatures have been obtained to be 307.85 and 338.15. And when we plug that in into our Clausius-Clapeyron equation, I have shown you what to plug in. I'm trying to solve the right-hand side right now, and that will come out to be 1.346. So I basically solved the 1 over T2 minus 1 over T1, and I've given you all the numbers here so you can work out the math on your own as well. The right hand side comes out to be 1.346. The left hand side is natural log of P2 divided by 100. So first of all, you need to take this out of natural log. I don't have much room here, so I'm going to move this all the way over here. In order to remove the natural log, you will have to use the anti-natural log, or second, in other words, the exponent of 1.346. So depending on your calculator, I have right now with me a TI-30X. What I did was I hit second natural log, which basically gives me e to the power of, and then I enter the 1.346, and that value comes out to be 3.842. I have another one which is a Casio, so I'm going to do it differently in there. So then all I'll do is I'm going to plug in 1.346 and then hit second natural log, so it automatically brings the e to the power of function, and that value comes out to be 3.846 as well. So we have the right hand side now, which is 3.842, and the left hand side is just P2 over 100. So if you wanted to determine the value of P2, all you have to do is cross multiply. So P2 will come out to be 100 times 3.842. So your final answer comes out to be 384.2 millimeter mercury. Notice again that as we are increasing the temperature, we expected the vapor pressure to rise as well, and it did. And if you think about it, ballpark temperature wise, we nearly doubled that. We went from a 34 degrees Celsius to about a 65-ish or so. So we nearly doubled it, and the vapor pressure is more than double the vapor pressure. So it's not, again, a linear relationship. It is, in fact, an exponential relationship between the vapor pressure and the temperature. Let's see what we have on the next slide. Oh, we have another one. The question is, the normal boiling point of benzene is 80.1 and the heat of vaporization is 30.8 kilojoules per mole. What is the boiling point of benzene in degrees Celsius on top of Mount Everest, where pressure is 260 millimeter mercury? So several things are given. We have the normal boiling point. Normal means that the external pressure is going to be 760 millimeter mercury. And so if this is T1, this is going to be P1. That's the delta H vaporization. I want T2, where the pressure is 260. So again, you can use Clausius-Clapeyron equation. Delta H vaporization over R. Notice I used a positive sign, so I'm going to use T1 minus T2. And again, you can use T2 minus T1, but then you have to introduce the negative sign. So however you want to set it. I'm just using a different version for a purpose here. just to show you that it really doesn't. You can use it one way or the other as long as you know what numbers go where. And so you have 260 over 760 millimeter mercury will cancel off. But I'm just still going to write it for the sake of argument. The kilojoules per mole, so that's joules per mole, over R is 8.314 joules per mole per Kelvin. That gets cancelled off. 1 over 80.1, you have to add 273 to it. Let's add only 273 this time. Of course, in the test, if it specifically mentions that you are supposed to add 273.15, then go ahead, do that. But for all practical reasons, you might be able to just use 273. T2 is what I'm seeking, so that value ultimately will end up in Kelvin. And if yes, they have asked in degrees Celsius, so we will have to subtract the 273 out at the end of the day. So let's solve this. So when you plug in P2, the value of that as 260 and the value of P1 as 760, your left side is panning out to be negative 1.072. 30800, which is what the delta H vaporization was in joules per mole, divided by the 8.314. That panned out to be 3706. So I have just plugged in the values and trying to calculate the final answer. And looks like there's barely any room here. Let me erase some parts. Oops. And when you solve the T2 completely, solve for T2, it comes out to be 48.5 degrees Celsius. And that makes sense. On top of Mount Everest, where the external pressure is only 260 millimeter mercury, any liquid is supposed to boil faster at a lower temperature. I gave you the example of water in Denver going from 100 degrees Celsius at sea level to 94. So Mount Everest is, of course, much higher. The decrease in the boiling point is going to be pretty dramatic. So your final answer is going to be 48.5 degrees Celsius. Now, I do want to say something here. Realize these are math-based problems, and your test is going to be multiple choice. At least 3 tests are multiple choice, so you don't have to show your work. I'm taking the time to solve every single step so that you can follow through and you don't make a mistake in an OWL problem or in a quiz or in a test. But realize you have to know how to go step by step, so that you can track if there's an error, you can track that.